Today, we're going to be talking about an introduction to polyphase power. And before we jump into three-phase systems, I want to go over briefly single-phase three-wire systems. I'm going to use this abbreviation 1, and then I think that's a Greek letter phi for phase, dash 3W for three-wire. Systems. So, single-phase three-wire systems are the type of electrical distribution network that is used in most residential buildings. It's also used in a lot of commercial buildings, and you may see it out in the street as well. So essentially, we talked about distribution systems with that picture at the very, very beginning of the class. So I'm going to introduce the schematic symbol for a transformer here, but we're not going to really get into the details of how transformers work or anything like that just yet. Just want to show you guys with some context of essentially what's going on, okay? So I've got essentially these three dots right here are just representing everything that's upstream from a distribution transformer. Then we've got our distribution transformer itself. So transformers are literally made from multiple coils of wire. So this picture right here is just trying to represent one of those coils. And this is going to be the primary side of my transformer. And the primary side of the transformer is usually on the source side of things. And then the secondary side of a transformer is connected on the load side of things, where our home and stuff like that is going to be considered the load. Okay. So I'm going to draw another coil over here. But this is going to be a special coil. Because it's going to include, let me move that up, a center tap. So I'm going to call this terminal of my center tapped secondary up here a lowercase a, where usually I use lowercase letters to indicate that we are on the source side of the system that we're looking at. And then I'm going to use uppercase letters in a little bit to indicate that we are on the load side of the system that we are interested in. So I'm going to have A on top, B on bottom, and N for neutral here in the middle. Okay. So if I were to, actually, let me just tuck it right here. So if I were to define this voltage, the nomenclature that I'm going to use is what's going to be called a double subscript notation, where the first letter of the subscript is corresponding to the positive polarity terminal of the voltage, and the second letter of the subscript is going to correspond to the negative polarity terminal of voltage. So I might call this voltage VAN, like so, where VAN would be 120 angle 0 degrees volts RMS. And then I'm going to define a voltage here that I'm going to call VBN. And it's going to be 120 angle 180 degrees volts RMS. And then these three terminals, the A terminal, the N terminal, and the B terminal, effectively represent the hot and neutral buses in a load center in our home. Okay. So what I mean by that is it's the part of the load center or the breaker box, as you might have heard it referred to, where we connect the electrical circuits that are used to wire up our home so that we can plug things into outlets and stuff like that. Okay. So this is the type of system that we usually have in our homes. And if I wanted to know this voltage here measured between the A terminals and the B terminal of my single phase 3-wire system, what do you guys think that that would be? So realistically, we could just perform Kirchhoff's voltage law around this loop and figure it out, right? So if we started down here, we would see the positive polarity terminal of VBN. So we would have VBN. Then we would see the negative polarity terminal of VAN next. So we'd have VBN minus VAN plus VAB is equal to 0, which means that VAB is going to be VAN minus VBN. So I gave you numbers for VAN and VBN, so I want you guys to throw them into your calculator and tell me literally what you get. Um, should be 240 angle 0. Yeah. So 240 with an angle of 0 degrees volts RMS. Because essentially what we're doing is we're saying 120 minus negative 120 is positive 240. Okay. So the voltage measured between the outside terminals in this single phase 3-wire system is going to be 240 angle 0 degrees volts RMS. And so that centermost tap on that secondary winding of the transformer, and I guess I should note that that's the secondary winding over here, divides the voltage, that 240 volts equally between those two tap points or on the transformer. Now, we don't necessarily have to have a center tap on a transformer. We could put the tap literally anywhere so that we can get any range of voltages for what we have access to on the outside terminals. But in our homes, it's always a center tap transformer so that we have access to both 240 volts and then two different 120 volt systems like that. Okay. So this is our single phase 3-wire system, how it's connected from transformer level and all of that kind of good stuff. Let's look at it from a more simplistic representation here, right? So treating the secondary terminals of our transformer as a voltage source, because that's effectively what they are to us as the end user, we might have a system that looks something like this, right? So here we'd have VAN, VBN, here's our A terminal, our N terminal, and our B terminal. And then if we had a simplified system where we had perfect conductors, meaning that our conductors, so the wires that we're using to connect our circuits and things like that, don't have any resistance, we would treat all of those guys as a short circuit. And so we might have some load here on our first circuit. I'm just going to call this ZL1. Here's our second circuit, a load on our second circuit. So I'm going to call that ZL2. And then we might also have a load connected to our 240 system, which I'm going to call ZL3, like so. So I'm going to label some currents on this diagram. And I want us to kind of figure out what's going on, okay? So let's call this current here IAN. So just to explain what's going on with our double subscript notation here. So this is the current that's flowing through our load that's connected between the A and neutral phase, or the A and neutral conductors of our three-phase, three-wire system. It's starting from terminal A and it's flowing towards terminal N. So the double subscript notation effectively for currents is, where does it start from is the first letter in the subscript, where is it flowing to is the second letter in the subscript. Then we might have a current here that I could call IBN. I might have a current flowing through this load that would be IAB. And I'm going to have my neutral current here that I'm just going to define as IN, like so. So if we were to apply Kirchhoff's current law at this central node here, this guy, what we would find is that our neutral current, IN, is going to be equal to negative IAN plus IBN, according to the directions that I have indicated, right? So we would have IN plus IAN plus IBN is equal to 0. All of the currents flowing in add together to make 0. And then I'm just moving everything that isn't IN to the other side of the equal sign to solve for that thing, okay? So let's look at what would happen. Let me actually move this up real quick. So let's say let's consider the case where our impedance ZL1 is, let's just throw something out here, 10 plus J6 ohms, and ZL2 is going to be 10 plus J6 ohms as well. So we would consider this to be a balanced case because the impedance seen between the A and the N terminal and the impedance seen between the B and the N terminal are literally the same thing. So I want us to figure out what our neutral current would be in this particular case, right? So how could I find the current IAN? And just to be clear here, this VAN is still 120 angle 0 degrees, volts RMS, and VBN is still 120 angle 180 degrees, volts RMS. Anyone have literally any thoughts? Yeah, 100%. So what's the voltage drop across that impedance ZL1? So maybe it would be helpful for now if I identified my different nodes and stuff like that. Okay. So that's all one node. That's all one node. And that's all one node. So my impedance ZL1 is between that red node on top and the green node in the middle. And my voltage source VAN is between the red node on top and that green node in the middle. What does that mean? That they're in parallel. Absolutely right. So what do we know about things that are in parallel? The voltage drop across them are the same. So what is the voltage drop across ZL1? Yeah, 120 angle 0. Absolutely right. So we would have 120 angle 0 degrees volts RMS divided by our impedance of 10 plus J6 ohms. And this would come out to be 120 over 10 plus 6I gives me a current of 10.2899. So let's call that 10.290 with an angle of negative 30.964 degrees. Amps RMS. Okay. So somebody else tell me what IBN is going to be. Exactly right. 120 angle 180 degrees volts RMS over 10 plus J6 ohms. And so I get 10.290 with an angle of positive 149.036 degrees. And taking these two things together, I would find my neutral current to be negative the sum of 10.290 angle negative 30.964 plus 10.290 angle 149.036. And I actually get an answer of 0 amps RMS. So when we have a balanced system like this, no current is going to flow along our neutral conductor. That's something that we're going to see pop up a lot. Effectively, what we're going to wind up finding, and I'll prove this here in a moment, is that the neutral conductor is going to wind up carrying any imbalance that we see in our system. Okay. So let's consider another case really quickly. Okay. I'll do this over here on the left. So let's say that our impedance ZL1 is once again going to be 10 plus J6 ohms, which means we don't need to bother calculating IAN because we already know what that's going to be. And our impedance ZL2 is now just going to be 10 plus J2 ohms, all right? So we know from the previous example that IAN is going to be 10.290 with an angle of negative 30.964 degrees amps RMS. Somebody else tell me how we'd find IBN for this guy. Yeah. So 120, angle 180 degrees, volts RMS divided by 10 plus J2. And what do we get there? I got 11.7669, so let's call that 11.767 with an angle of 168.6900. And our neutral current in this case is still going to be just negative IAN plus IBN. So negative, what I have in my calculator is X plus Y. I get 4.036 with an angle of 47.77, excuse me, 726 degrees amps RMS. So our neutral conductor is now carrying some amount of current, and because our system is unbalanced, we don't have the same impedance connected between the A and N terminals as we have between the B and N terminals. But we could also see that our neutral conductor is carrying less current than the A phase conductor or that B phase conductor, right? So IN is much less than the current IAN, and it is less than the current IBN. So it's for this reason that your neutral conductor can technically be a smaller size than your phase conductors, okay? So this is a simplified system, okay, where we're dealing with perfectly conducting wires and all of that kind of good stuff. Let's look at what would happen if we had a system that didn't consist of perfect conductors. Okay. I'll let you guys continue to copy this before I move on to the next page. All right. So a more realistic representation of a three-phase, three-wire system, or excuse me, a single-phase, three-wire system might be something like this, right? So here's my voltage VAN again. Here's my voltage VBN again. This is my neutral conductor. Here's my A phase and B phase terminals. So we might have an impedance here. Where this is representing the total impedance of the wire that's going out from our breaker box out into our home, connecting to one of our circuits that contains all our outlets and all of that kind of good stuff, right? And I'm going to choose to put a capital A on this side, representing that now we are on the load side of our system. Similarly, my neutral conductor, so my neutral wire, might have some impedance as well. So I'm going to call this Z neutral. And down here, I'm going to have another Z wire impedance, like so. Between the A and capital A and capital N, I might have my impedance ZL1. So that's my load on circuit 1. Down here, I might have another impedance ZL2. And then between the A and B terminals, I might have a load representative of a 240 volt circuit. So something like an oven, a water heater, etc. And I'll call this guy ZL3. So this system is a bit more complicated. And because we have all of these impedances like this, we're not going to be able to tackle it as easily as we did where all of our wire impedances were considered to be negligible, right? So if we had a system where, let's say, I had Z wire was equal to 0.1 plus J 0.08 ohms. Z neutral was equal to 0.6 plus J 0.01 ohm. ZL1 had an impedance of 8 plus J2 ohms. ZL2 had an impedance of 11 plus J4 ohms. And let's say ZL3 has an impedance of 22 ohms with no imaginary part. How might we go about solving for, let's say, the complex power absorbed by load 2? So let me ask you guys a question. Are you familiar with the technique of mesh circuit analysis? Okay, a little bit. All right. So we're going to practice it here. Did you guys ever have to do any mesh circuit analysis using complex numbers in your previous class? Okay. What did you use to solve those systems of equations? Anybody remember? So in my experience, I usually wind up using a computer because my calculator literally can't solve a system of equations that has complex numbers in it. So I use a computer algebra solver, something like MathCAD. Okay. I believe, but let me double check here. Okay. So let me just check on Canvas real quick, like. I may be telling tales out of school here. Yeah. So there's been a download link available for you guys to get MathCAD Prime 8.0 here since I believe the first day of class. If you haven't already downloaded it yet, you'll probably want to do it sometime in the relatively near future, but I am recording all of this. I'm going to talk our way through things pretty easy and all of that kind of stuff. So you'll have access to this video hopefully later today so that you can follow along at your leisure. Okay. So before we even get into the MathCAD stuff, I'm just going to open it up because it takes a minute for it to get cracking. We are going to perform our circuit analysis here, okay? So I'm choosing to use mesh analysis in this particular case just because this system only has 3 meshes, and it has a whole bunch of nodes. So the mesh circuit analysis is going to be an easier system to set up. I'm going to define my mesh currents. So here is going to be my mesh current I1. Let's call this guy I2. And let's call this guy out here I3. And for what it's worth, I'm just going to set things up symbolically because I can put all of this information into the computer and let it handle everything for me. And then I could test other cases and all of that kind of stuff as well. Okay. So do any of you guys remember how to apply the mesh analysis technique? Let's start there. You said you've experienced it before, used it before, so tell me what to do. So the ultimate goal of mesh analysis is to find those 3 mesh currents. Absolutely. But how did you set up your system to be solved? So I1 plus I2 is equal to I3 is incorrect. Okay. So mesh analysis is setting up multiple different Kirchhoff's voltage law equations and then using that system of Kirchhoff's voltage law equations, you solve that system to get those mesh currents, okay? So you guys don't seem super familiar with it, so let's go through the steps, okay? I'm going to follow each of those currents around their clockwise path, starting from the bottom left-hand corner of each of those paths, and then I'm just going to keep going until I get back to where I started from, okay? So anytime that I see a voltage source, if I see the negative polarity terminal first, I'm going to give that voltage a minus sign. And if I see the positive polarity terminal first, I'm going to give it a plus sign, okay? So if we start with our KVL at mesh 1 relationship, so I'm starting here and I'm going up, okay? The first thing I see is the negative polarity terminal of this voltage source. So my first term is just going to be negative VAN, okay? I've gone through my voltage source. So now I'm going through that impedance Z wire as I'm following that loop clockwise around this mesh. And so I'm trying to express the voltage drop across that impedance Z wire in terms of any mesh currents that flow through it. So what's the only mesh current that flows through that Z wire that I have the black arrow pointing to? I1, okay? So using Ohm's law, I'm just going to have plus Z wire times I1. So we've taken the voltage drop across that Z wire. Now we're trying to find the voltage drop across this impedance ZL1. So there are two mesh currents that are flowing through ZL1, right? So because ZL1 is shared between mesh 1 on the upper left-hand corner and mesh 3, which is the right-hand half of the circuit, we are going to see some combination of mesh currents 1 and 3, okay? So my current I1, as it goes around its clockwise path, is in the same direction as that arrow that I drew. So it's going to wind up getting a plus sign. And I3, as it flows around its clockwise path, is actually going to flow up through ZL1. It's in the opposite direction, so it's going to get a minus sign. So my voltage drop across that guy should be plus ZL1 times I1 minus I3. Does anybody have any questions, comments, or concerns about where those currents came from or why they have the signs that they have? Okay, so if nobody has any questions about that, then I want you guys to tell me what the voltage drop across my neutral conductor should be. Exactly right. So our impedance Z neutral times I1 minus I2. And now we're back to the point where we started from. So I'm just going to set all of this equal to 0. So that's my first KVL equation. And now we're going to start on our second KVL equation, which I'm going to write around mesh 2. So I'm starting from the bottom left-hand corner because that's just where I like to start things. So what's the first thing that I see? VBN, okay, and I see the positive polarity terminal first, so I should just have plus VBN, so I'm just going to start with a VBN here. Now, I'm going to have the voltage drop across the neutral impedance, and I'm going from left to right. So what should that voltage look like? So you're close. You got your, goodness. What the heck happened? There we go. So we have Z neutral. So you said I1 minus I2, okay? So I1 minus I2 is the current that's flowing from right to left through that guy. I'm looking for the current that's flowing from left to right, so I should just swap the order. Exactly right. So it'll be I2 minus I1. So if it's not obvious, and it's okay if it isn't, when we are following essentially our mesh current 2 around this loop, so when we're applying KVL at mesh 2, all of our I2s should wind up having a positive sign if I choose everything in a clockwise fashion. Just like when we did our KVL around mesh 1, all of our I1s had a positive sign, okay? So Z neutral times I2 minus I1. All right. So I'm going to stop drawing arrows. What's the next thing that we would see? ZL2. Exactly right. And then somebody else tell me what's the last term in this expression. Plus Z wire. And what's the impedance flowing through this Z wire, Mark? Or I think I said what's the impedance? What's the current flowing through that impedance? I2. Exactly right. Okay. And we're back to where we started from, so we're good to go. And then lastly, we have our KVL at mesh 3 systems. So starting from the bottom left-hand corner, what's the first thing that we should have? ZL2. And what will the current for that impedance ZL2 be? I3 minus I2. Great job. What's the next thing that we're going to have? ZL1, okay. And then what's the current flowing through ZL1? I3 minus I1, thank you. And then lastly, we're going to have what? ZL3. And what's the current flowing through that guy? I3. Great job. That is equal to 0. All right, so before we move on from here, I want to make a quick note here, right? So how many of you guys have ever opened up your breaker panel? Probably most of you. How many breaker switches are usually in there? Probably a lot more than 3, right? But all of those breaker switches are going to be connecting circuits either between this capital A and capital N, or capital B and capital N, or capital A and capital B, meaning, so if your breaker has 2 poles on it, so if it's twice as large, it is one of those 240. It's a breaker for 240. If it's the single slot, it's a 120 breaker. So realistically, even though we only have 3 little circuits connected here, so one impedance between A and N, one impedance between B and N, and one impedance between A and B, we could actually use this model to do anything in our home. Because if we had a second circuit connected between A and N, that's just going to be in parallel, and we could lump those 2 impedances together if we were so inclined to find that voltage drop and things like that, right? So this looks, it's a little bit more complicated than the ideal case we had up here, where all of our cabling effectively had no resistance, but we can still use this guy to represent even the complex system of a whole home that's wired up or something like that on a 3-phase, or excuse me, a 1-phase 3-wire system. Okay. So just wanted to bring that to your attention. All right, so what I'm going to do now is I'm going to set things up in MathCAD. Understand completely if you guys haven't yet downloaded it, installed it, and all of that kind of stuff, you won't be able to follow along. That's okay. Like I said, I'm recording things. You can follow along later at your own pace, but I will try to explain as much as I possibly can while I'm doing this, so that if you have to watch the recording, you'll know what's happening. So the first thing that I'm going to do up here at the very top is I'm literally just going to set up all of those constant terms. So for those of you, actually all of you should have some experience with programming and all of that kind of stuff from your previous classes, right? So essentially what I'm doing when I put all of this stuff here is I'm like creating a bunch of global constants that can be used everywhere inside this worksheet. So I'm going to start with VAB. So what it's worth, let me go through this slowly just in case you're not familiar with MathCAD. Sorry, I don't know why the hell it looks like it's opening another version of it. So capital V, that's fairly obvious where I got that from. If I press Control and then minus, that allows me to do subscripts. So I'm going to have AB, and then I'm going to press Shift and colon, and that's giving me this colon equal sign. So this is how I give variables a value or something like that. I'm going to do 120. So open parentheses, 120. And then I need to do the angle operator. If we look here in the operator menu and look under engineering, we can see that we can click this button to give us the angle operator, but I find that to be a pain in the ass. There is also a keyboard shortcut that's given that says Control Shift P. So that's what I'm going to actually press to give me that angle operator, okay? So Control Shift P gives me the angle operator. Now I'm going to type 0. If we go back to that operator menu and go down here, we can see that the degree symbol is available to the left of that angle operator sign, but there isn't a keyboard shortcut for that. That annoys me. So instead of having to go up there and click that every time, I'm just going to type in the letters DEG, and MathCAD will know to interpret that as an angle that is measured in degrees. By default, it will do everything as angles that are measured in radians. And so if you don't explicitly tell it degrees, you'll run into issues, okay? Outside of these parentheses, I'm going to type Shift and then 8, since it's literally just multiplication. And I'm going to give this a unit of volts, which is just a capital V, okay? And I'm going to do a similar thing for that voltage VBN. So VBN is going to be 120 angle negative 180 degrees volts. And I've got my two voltages declared. Okay. So just to recap there, I get my subscripts by pressing Control minus. The angle operator is Control Shift P. Since there isn't a keyboard shortcut for a degree symbol, I just type the letters DEG. And I know this is going to seem weird, but I'm always going to explicitly multiply my unit times that complex number, because sometimes MathCAD can be fickle and it will treat stuff inside a parentheses as if it's a function when I don't want it to be. If I explicitly multiply by the unit, it never does that, so that's why I'm doing this. Now I'm going to set up my impedances, right? So I have an impedance of Z wire, and I think that that was 0.1 plus, let me go back here real quick and look, J 0.08. So I'm going to enter that in as 0.08 J. I need to put the J afterwards, otherwise it is not going to correctly interpret that. So if let me just show you real quick here. If I did J 0.08, notice that that J is italicized. That means it's treating that J as if it were a variable. When I put it at the end, it's not italicized, so it is treating that J as if it is the imaginary operator, the square root of -1. You could just as easily put I there and it would treat it the same way, because MathCAD has both I and J built into it. If I press the space bar a couple of times, I've highlighted everything, and I'm going to put parentheses around this because it's a complex number. And now I'm going to multiply by the unit of an ohm, okay? So this is another thing where we're going to use a keyboard shortcut, but I want to show you where it's coming from. So if I press the symbols key here and I go down to uppercase Greek, it tells me that the keyboard shortcut for capital Omega is having a capital W and then pressing Control G. So essentially, this is wildly dumb. Since lowercase omega looks like a lowercase w, uppercase omega uses uppercase w. And then Control G is just telling it to convert to Greek. So I have capital W, and then Control G converts that capital W into a capital omega, which is our ohm unit. Okay. And then I'm going to go ahead and do that for my neutral. So let me remind myself of what that number was. 0.6 plus J 0.01. Multiply by omega. And then the L1 was 8 plus J2. ZL2 was 11 plus J4. And lastly, ZL3 was, I think, just 22 ohms. Yeah. So those are all my constants. Okay. So now I'm going to use what's called a solve block in order to solve the system of equations that we developed when we did our mesh analysis. Okay. So up here where it says guess values, this is effectively where I'm declaring the different variables that I'm going to try to solve for. So in this case, that's going to be I1, I2, and I3. And I literally need to guess a number for it to start from, okay? So it solves things using an iterative process where it just constantly runs the numbers over and over and over again until it comes up with a solution. And if I don't give it somewhere to start from, it won't literally start, okay? So I'm going to have a current of I1, and I'm going to just start at 1 angle 0 degrees amps. That's my usual guess value is the number 1. So 1, Control Shift P, angle 0 degrees, multiply by an amp. I'm going to use this exact same guess value for I2 and I3. So I've got the 3 variables that I'm trying to solve for declared. Now, down below this, and for what it's worth, this constraint area thing is going to expand to take in wherever I happen to put. But in the constraint section is where I'm going to enter in the equations that we developed, right? So my first equation was negative VAN, and then I had plus Z wire multiplied by I1. Then my next term was ZL1 multiplied by I1 minus I3. Then I had Z neutral multiplied by I1 minus I2. And I'm going to do control equal 0. So notice that this has like a bold face equal sign. That's effectively meaning everything on the left-hand side of this equal sign must be equal to everything on the right-hand side. And those are the equations that it's actually using to solve that system, okay? So that's my first equation. My second equation, and if I type in something wrong or if I'm misremembering, please correct me, was going to be VBN plus Z neutral multiplied by I2 minus I1. Then we had ZL2 times I2 minus I3. And then we had Z wire times I2. And this will be control equal to 0. And for our last equation, we had ZL2 multiplied by I3 minus I2 plus ZL1 multiplied by I3 minus I1 plus ZL3 multiplied by I3 is equal to 0. I'll give you guys that are following along a moment to catch up. I know that you're not used to doing this as much as I am, so you're probably not typing it in as fast and all that jazz. So the next thing that I'm going to do, and this is technically optional, but it is very good practice, and I'll explain why in a moment, is I'm going to put a matrix in over here in the solver area. Because I'm solving for three different variables, I1, I2, and I3, I'm going to put a 3x1 matrix. And what I'm going to do is I'm going to put in I1, I2, and I3 in those spots. And then I'm going to press Shift equals. So essentially what I'm doing when I put that matrix there is I'm telling MathCAD to store the results of the find operation that I'm about to do in that matrix so that I can use those values outside of the solve block to do further calculations, like the complex power calculation we're going to do here in a moment. Okay. So I'm just going to type now find, and then I need to put all of the variables that I'm trying to find, I1, I2, and I3, in the order that I wanted them, that I defined them to be stored in that matrix. So I1, comma, I2, comma, and then I3. And when I press just regular equal sign here, it's going to spit out after it thinks about things for, oops, it's giving me an error right now because I have this as VAN, but up here I accidentally said this was VAB, so I need to fix that. And there it goes. Sorry for that typo at the literally the very first thing I put in, had a typo in it. Son of a bitch. So it gave me results in rectangular form. Okay. We can fix this by going into the math formatting tab. And if we look at this little block right here, in the bottom right-hand corner is where we can change our complex values. So MathCAD gives us the option of expressing our answer in rectangular form with I as the imaginary operator, rectangular form with J as the imaginary operator, polar form with our angle expressed in pi radians, polar form with our angle expressed in radians, and lastly, polar form with our angle expressed in degrees, which is what we typically use. So I'm going to choose that last option from the drop-down menu, and there is my three currents expressed in polar form. Okay. So if we go back to our schematic diagram, I asked specifically for us to find the complex power absorbed by impedance ZL2. Okay. And we just found, actually, so let's talk about how we might determine that. Okay. So anybody have any thoughts? We've done mesh analysis, so we have all three of those currents available to us as known quantities now. All right, so you guys are quiet this morning, so I'll talk our way through things here really quickly. So I want to define a couple of things here. I'm going to define them in purple, I guess. So let's say that this is the current that's flowing through that impedance. So I'm going to call this IL2, right? And this will be the voltage drop across that impedance, which I'm going to call VL2. So according to our definition for complex power, we could find this as VL2 multiplied by IL2 conjugate. That's one way. If we remember from our alternative relationships, we could also say that this is going to be the magnitude of VL2 squared divided by ZL2 conjugate, or this could be the magnitude of IL2 squared times ZL2. Any one of those three different equations will give us the complex power that we're looking for. So, which one do you guys want to use? Let's start there. The first one, okay? So we are going to need to figure out what VL2 and IL2 are based on the results of our mesh analysis, okay? So let's start with IL2. What should IL2 be? I2 minus I3, exactly right. And then what would VL2 be? It's the voltage drop across ZL2. In purple on the left-hand side of. So it won't be VBN, because if it were VBN, then we would be saying that there's no voltage drop across our neutral conductor and there's no voltage drop across that Z wire. And since they have finite impedance, we can't make that assumption. We know the impedance, we know the current. Why can't we just use Ohm's law, right? So that would be just IL2 times ZL2. So I'm going to put those relationships into my math CAD sheet. Give me just a second to text my wife because the vet's calling me and I want her to call them because I'm in class. All right. So, oh wait, I need my keyboard for this. Down here outside of the solve block, I'm just going to write a new equation that says that IL2 is I2 minus I3. Yes.
So the KVL equations, you have it equal to zero. Remember, I put in the equal sign and just solves it out.
What equal sign are you using?
The one with the plus sign over it.
But are you doing control equals to make it look boldface like this?
No.
That's, you need to use that control equal.
That's how that works.
Okay. So IL2 is I2 minus I3. And then I'm just going to press a regular equal sign here. So it'll give me a number, 10.253 angled negative 20.553 degrees. And then VL2 is IL2 multiplied by ZL2. So I get 120.006 with an angle of negative 0.57 degrees volts. And then lastly, I'm going to calculate my complex power. SL2 is going to be VL2 times IL2. And I need to make IL2 conjugate. So if I go back to the math tab and I go to operators, I think this is where it is. Yeah, the first option under engineering is the complex conjugate. So the keyboard shortcut for that is Control Shift open parentheses it's not going to put an asterisk next to it like is traditionally done to denote that operation. Instead, it's going to put a bar over it. So if I press Control Shift P, or excuse me, Control Shift 9 for open parentheses, I get VL2 times IL2 bar, where that bar means the complex conjugate operation. And I get a result that is 1.23 times 10 to the 3 angle 19.983 watts. So it's going to use watts for everything, but we know that complex power is measured in volt amperes. Because I have times 10 to the 3, I'm going to put it in kilowatts. So 1.23 angle 19.983 kilowatts is our complex power. Okay. If we wanted things in rectangular form, I could just do SL2 is equal to, let me just scooch this over, put it in kilowatts again, and I'm just going to tell it specifically to give me the result here in rectangular form so that I can now see what my average power, reactive power, etc. are. Okay. Okay, I think this is enough on single phase 3-wire systems. We've done a simplistic example, we've done a complicated example. I've shown you guys how to use MathCAD to solve systems of equations using complex numbers. So let's start talking about 3-phase systems and all of that kind of stuff now. And if you have any questions about any of this, I would be more than happy to answer them after we get out of class. All right. So let's call this part an introduction to 3-phase circuits. So up to this point, most of the circuits that we have analyzed in this class have been a single phase circuit, okay? And so I'm going to draw a representation of a single phase circuit here pretty quickly. So we might have something like this. So I have my voltage source. And I'm going to label this as VP with an angle theta V. So that just stands for a phase voltage. Okay. I'm calling this terminal lowercase a. I'm calling this terminal lowercase n. And I'm going to put a dashed red line through this. And everything to the left of this dashed red line is the source side of our network. Here in the middle, I'm going to give myself an impedance that I'm going to call ZW, which is the impedance of the wire that I'm using to connect my source to my load here, which will be on the right-hand side. I'm going to call that terminal capital A. And then down here on the bottom, I'm going to give myself an impedance ZN. Let me put that on top, actually. And this is the impedance of my neutral conductor that connects my source to my load. And as we saw in the last example that we worked, those two impedances, our wire impedance and our neutral impedance, don't necessarily have to be the same things. So I'm giving them different names so that that's attempting to be obvious there. So here is another dashed line. I'm going to call, because I forgot to label it, this terminal capital N. And this is my transmission line network. That I'm using to send power from the source to my load. And then lastly, on the right-hand side, I'm going to have my load impedance, ZL. So this is a generic single phase 2-wire system. So if your house or residence only has access to 120 volts, this would be representative of what's going on in the place that you're at. Okay. So I want to now draw a 3-phase system. Okay. And so this is going to be a little bit more complicated looking. Actually, it's going to be significantly more complicated looking, but it's going to have the same basic parts. Okay. So here I'm going to draw a voltage source between my A terminal this is going to be my neutral connection on the source side of things. Here's a voltage source connected to my B terminal. And then here's a voltage source connected to my C terminal. And for right now, I'm just going to call this guy VP angle theta lowercase a. So this is just my phase voltage, whatever it happens to be. And the angle for my A phase. This is going to be my phase voltage with an angle of theta B, where I'm assuming that theta A and theta B are different numbers. And then lastly, down here, I'm going to have VP with an angle of theta C. So this is my 3-phase source. This is one of 2 possible representations of 3-phase sources that we're going to see. This guy is what's technically called a Y-connected source. And then here in the middle, I'm going to have my transmission line network again. So I'm going to have an impedance ZW between the lowercase a and capital A terminals. I'm going to have an impedance of ZW between my lowercase b and capital B terminals. And I'm going to have an impedance ZW between my lowercase c and capital C terminals, like so, where these guys are once again making up my transmission line network. So what I'm using to send my power over some distance. And then lastly, over here on the right, I'm once again going to have a load. And this is going to be a 3-phase load. So I'm going to call this ZLA. ZLB. And lastly, ZLC like so. And I'm going to tie all of these guys together at this side with a capital N terminal for the neutral on my load side. So let me just make a note here. This is a generic three-phase, three-wire YY system. So three phases because I have three different voltage sources, each having a different phase angle. It's three wire because we are connecting the source to our load with three transmission lines, one for each phase. We could also have a three-phase four-wire system where we have a specific neutral wire that's connecting our source to our load as well. This is a YY system because our source is connected in a Y configuration. We'll go into that a little bit more in a bit. And our load is also connected in a Y configuration. So my question to you guys is, why do we use three-phase systems for large-scale electricity distribution here in the US, in Europe, and effectively every industrialized nation? So let's address this more power thing that was said, okay? So more power. So let's say that ZL in our single phase system is absorbing the exact same amount of power as ZLA, which is absorbing the exact same amount as ZLB, which is absorbing the exact same amount as ZLC. So we have more power in our three-phase system because there are three loads absorbing the same amount of power. Okay, so that's reasonable. That's not necessarily the reason why we would send it in three-phase. That's just a consequence of us using three-phase. If we've got these three different loads and they're all identical to our single-phase load, because there are three of them, we will be sending three times as much power. Okay. So I know this is going to sound kind of silly, but how many wires were used in our single-phase system? Literally described it as a two-wire system, one for our wire and one for our neutral. So those are two different wires that are used there. How many wires are used in our three-wire system? Three. Yay. Okay. So essentially, we're able to send three times as much power with only 1.5 times as many wires. So it is literally cheaper. It's cheaper to set up the infrastructure to do three-phase systems than it is for single-phase systems to send the same amount of power or electricity. So always, always, always the defining characteristic of why things are done a particular way is going to be cost. Everything is a business. Everybody wants to make money as best as they can. And so if it's cheaper to do it one way, that's the way that it's going to wind up being done. 99.99% of the time, okay? So three-phase systems are used because it's cheaper to send lots of electricity in a three-phase system than it would be to do it in a single-phase system, okay? We can always branch off of any part of our three-phase system to make it look like a single-phase system if we need just single-phase connections for specific things like our homes, businesses, etc. Okay, and we'll talk about how that works in a little bit. Okay, another reason why three-phase systems are commonly used in industrial settings is because three-phase electrical, rotating electrical machinery like induction motors, synchronous machines, and things like that, if we connect, there are single-phase motors, single-phase synchronous machines, but those single-phase motors, when they absorb power, it's not constant. And so we wind up getting a lot of variability in the torque that can be produced by these machines. which in some applications is okay, and in other applications is very, very bad. In a three-phase system, we'll see this here probably by the end of next week. The power that is delivered to these three-phase machines is going to be constant, which means they're going to generate a constant torque. And so those machines are going to last for a really long time because they experience the smallest amount of vibration that we could expect of them. So there's going to be significantly less mechanical wear and tear on a three-phase motor than there will be on a single-phase motor because the torque it generates is constant. So that's why three-phase systems are used in so many industrial settings. So I want us to look briefly at how three-phase voltages are generated. Okay. So I'm going to try to draw a picture here, and I'm going to pre-apologize for how utterly shitty this is. Okay. So this is going to be a very simplistic representation of a synchronous generator. Okay. You'll learn much more about synchronous generators in your ELET 360 class that you'll take next winter. But effectively, practically all electrical rotating machinery is consistent or consists of two parts. Okay. So the first part that we're going to have is what's called the stator, and this requires me to be able to draw concentric circles, so this is going to go very poorly for me. I'm just giving you a fair warning of what I'm trying to do. That circle doesn't look too shitty. And now I need to put another one around it. So this is our stator. And this is the stationary part of a rotating electric machine. Okay. So on a stator, we are going to have three different phase windings, and these are literally just coils of wire. Okay. So I'm going to try to kind of draw these things. So this guy right here, this little box is going to be where my A phase slots in. And I'm going to do this guy in black. Okay, so that's just a little circle there for my A phase. And then 180 degrees away from this guy, I'm going to have an A prime. So if current is flowing into this A bit, current then has to flow out of A prime because that's kind of the return path for that current. Okay. And I'm going to do my return path in gray. Okay. Now, physically, 120 degrees away from this A phase terminal, I'm going to put my B terminal. So that should be somewhere in the ballpark of here. And I'm going to choose to do this guy in blue. And 180 degrees away from that B, I'm going to have my B prime return path. I'm also going to do it in gray. And then 120 degrees away from our B, path, we're going to have our C path over here, which I'm going to draw in red. And then 180 degrees away from that guy, I'm going to have my return path for C, which is going to be indicated by C prime. So that's my stator, and now I'm going to show how these different parts of this thing are wired together, okay? So I'm going to have access to this A terminal. So that's going to be the A terminal for my voltage source. I'm going to have access to my C terminal. So that's going to be where I access the C phase of my system. I'm going to have access to my B. Like so. And then I'm also going to wire all of those return paths together. And so this is going to be my neutral. That looks too much like an H. Jump that over. Jump that over like so. And so this is what's called a Y-connected stator, okay? So essentially, when I have access to those three terminals, I will have access to the following three voltages, okay? So I'll have a VBN, so that's the voltage measured between the B terminal of my stator and the neutral terminal of my stator. I will have access to a voltage VCN between my C terminal and my neutral terminal. And then lastly, I will also have access to a voltage VAN. So that's between the A terminal and the neutral terminal, like so. Okay. So those are my connection points. Now I need to draw what's called my rotor. Okay. And I'm going to do a very simplified representation of my rotor. Okay. So my rotor is an electromagnet. And I'm going to choose to represent that with a bar magnet. Okay. So this is going to be my north pole of my bar magnet. This is going to be the south pole of my bar magnet. This dot here in the middle is the point of rotation for this bar magnet. And I'm going to spin this guy at some angular frequency omega. And so have you guys had physics class having anything to do with magnetic fields or anything yet? Great. Okay. So what happens when the flux that's seen by a coil changes? Anybody heard of Faraday's law of electromagnetic induction? So Faraday's law of electromagnetic induction says that whenever the flux through passing through a closed path changes, we're going to induce voltages and currents, essentially. Okay. So we have three different coils here. And as that permanent magnet spins, the flux that each coil sees is going to change sinusoidally, which means we are going to induce sinusoidal voltages. So the way that I have drawn this particular magnet through the middle here is such that the flux that's passing through the A coil is going to be at its maximum. So if I were to try to plot these three waveforms, it would look something like this, okay? So in black, I'm going to do my voltage VAN, okay? So because my flux is at its maximum, it's going to start at its maximum value. And I give myself, let me make this slightly longer. I'm going to generate some sinusoidal voltage like so, where this maximum value is my phase voltage, VP. Yeah, so I'll just leave it like that for now. Okay. For my B phase, so because my A phase is 100, excuse me, it's vertically oriented right now, right? My B phase is physically 120 degrees out of phase. So after my bar magnet spins by about 60 degrees from what I have right now, I should see that the B phase of my voltage is going to be at its maximum. So it's going to happen effectively a little bit later in time, right? So we might have our B phase hitting its peak value, let's say roughly here. And then because my C phase is 120 degrees physically from my B phase, it's going to hit its peak value in time a little bit later as well. So loosely, we're going to have a situation that looks something akin to this. Okay. So we're going to have these three voltages all sinusoidally oscillating, and they're going to be exactly 120 degrees out of phase with each other. So in the time domain, we might have VAN as a function of time would be VP times the cosine of omega t plus 0 degrees. VBN as a function of time would be VP cosine omega t minus 120 degrees. And VCN, actually, I don't need those tildes over them because these aren't phasors, they're time domain things. Sorry about that. Would be VP cosine omega t minus 240 degrees. Okay. So there is exactly 120 degrees of phase separation between each of those phases because the coils are physically oriented to be 120 degrees out of phase with each other. So we could come up with, 4-phase stators and 6-phase stators and 8-phase stators, and in some applications, that kind of thing is used. But the most generic type of system is going to be a 3-phase system like this, where all three of our phase angles are separated by exactly 120 degrees. This is what we're going to call a positive phase sequence system, meaning that A hits its peak, and then B hits its peak, and then C hits its peak, and so on and so forth. If we had a negative phase sequence system, C would hit its peak first, then B, then A. So literally that just means our magnet would be spinning in the opposite direction. Okay. And we can make that happen in any three-phase system literally by just switching the B and C wires. It'll spin the other way. Or the voltage generated will be in a negative phase sequence. Okay. So we only have a couple of minutes left here. So I just want to talk about some things. The 120 degrees of phase separation, and I feel like I'm beating a dead horse here, but it is important. That is going to happen because of the 120 degrees of physical separation between those coils. Now, what's going to make the value of those phase voltages VP the same for all three phases? Anybody have any thoughts? So the frequency is going to have something to do with it. All three of them are going to experience the same frequency because it's just that single rotor that's spinning at one angular frequency omega that is inducing those voltages. So that is definitely part of it. All of the coils have to be constructed the same in order for them to be to have the same voltage induced across over them. So in modern generators and stuff like that, where they are literally constructed by robots, this isn't an issue. They are all going to be practically identical, meaning that it's going to be the same total length of wire, plus or minus a couple of millimeters tops. There's going to be the same number of turns in each of those coils. So everything is set up so that all of our three-phase voltage generators are going to give us a balanced set of voltages, meaning that they're all going to have the exact same magnitude, and they're all going to have exactly 120 degrees of phase separation. So if we were to represent these guys as RMS phasors, this will be the last thing that we talk about today. My RMS phasor voltage, VAN, would be expressed as, let's say this is going to be V effective with an angle of 0 degrees, volts RMS. VBN would be V effective angle negative 120 degrees, volts RMS. And VCN would be V effective angle negative 240 degrees, volts RMS. So I want you guys to add those three things together. So just use literally the number 1 as V effective and tell me what you get. One angle 0 plus one angle negative 120 plus one angle negative 240. What do you get?
0.
Yeah, so 0. So in a balanced system, if we add all those voltages together, we're going to wind up getting 0, which hopefully should make a little bit of sense. Remember when we added our currents together in that balanced single phase 3-wire system, we found that our neutral current is 0. We're going to get lots of zeros. It's going to wind up making the math easier as long as we're dealing with balanced systems, okay? So that's enough out of me for today. What we are going to start talking about at the beginning of our class meeting on next Thursday is the different possible configurations that we might have for both our source and our load, and then we'll get into some analysis. You guys should expect a homework from me on single phase systems, either sometime later today or tomorrow, and it will be due next Tuesday. So you'll have a full week to work on it. It'll probably be somewhere in the ballpark of 5 problems, and at least one of them will be a single phase 3-wire system that requires a computer to solve it like we did today, so that you get a little bit more practice. Does that sound reasonable? A week to do 5 problems? Okay. Good deal. Thank you guys for your attention. I'll see you on Thursday.